Hi everyone, I've got one more example on using properties of definite integrals. If you haven't already, make sure you use this one to pause and try and do some on your own, and then just check back if you're not sure. This one does throw a little bit of a twist in it by putting the square here. That's not really that big of a deal. I would just like to point out that the integral from a to b of f of x squared is not the same as the integral from a to b of f of x dx squared. So squaring the function doesn't just straight up square the area. It's a little bit more subtle than that, so we are going to need to be careful. Okay, so with that warning in mind, I can erase all that mess. Let's see, we are given the integral from a to b of f of x. We are given the integral from b to c of f of x. We are given the integral from a to b of f of x squared and the integral from a to b of g of x. Okay, so this first one is only asking about f of x, so I think those two that I circled are it. And a to b, b to c. So I think all we are looking at here is that we have a property that says if you go from a to b and then you go from b to c, it's exactly the same as going from a directly to c. And again, what's cool about this is that's pretty obvious if b is between a and c, but it works even if it's not. So even if you go from like 0 to 10 and then you go from 10 to 3, it's still going to give you the right answer because going backwards will just subtract off any extra area you've captured. And we know that the integral from a to b is 9 and the integral from b to c is -7. So it looks like the area under function f from a to c is going to add up to 2. The positive and negative areas will add up to 2. Okay, so for b, and this is getting at what I said earlier, we do need to be a little bit careful. Those two are not the same thing. So we're going from a to b. And we want, okay, so I think we're going to want this one, and we're going to want this one. So I know from above that the integral from a to b of f of x squared is 36. So that's completely legitimate to just plug in. That directly replaces this. Where I need to be careful is right here, and it's not that hugely careful, but this says first integrate function f from a to b and then square. So we integrate, we get 9, we square. That's the order. So this one says square and then integrate. If we don't know the function, that's tricky, but we were given the information. This one says integrate and then square. So I have 36 minus 81, 80, 70, 60, 50, 45. Negative 45. 76, 81. Yep. Okay. So negative 45 on that one. Next, 2 times f of x minus g of x from a to b. So I think I'm eventually going to want the integral from a to b of f and the integral from a to b of g. This is my prediction. Okay, so I'm going to scoot a little bit and then I'll come back down. What I am seeing is that I can use properties first to split this up. Again, be really careful. There's order of operation stuff that a lot of people, even at this point, make some big mistakes with. So we want to focus on the big operation, which would be the last thing that you actually do. So here, the very last thing I would do is subtract, so that's the first thing I would focus on. If you don't do things in that order, if you try and separate the 2 out, put it out in front right away, you're going to have to multiply the g by 1/2 to cancel that out, because all of a sudden you're forcing a 2 to apply to the g that did not apply to the g. The g of x part is great. I would like to do a little bit more work on the f of x part. So I'm going to have 2 move out in front finally. I know that the integral from a to b of g of x is -2, so it's minus a -2. And I also know that the integral from a to b of f of x is 9, so I get 2 times 9 plus 2 19, oops, not plus, equals 20. Okay, switch colors again. D is similar, but people make a lot of mistakes with the 2 in this one. So first step, I would say, is pretty much identical. Integral from a to c of f of x dx plus the integral from a to c of 2 dx. What people mess up is thinking that 2 can just completely separate out without being integrated. That's not true. It's not like above where you're multiplying by 2 and you're saying that if you double the height, that's the same as doubling the overall area. Here, we're actually shifting the function vertically, which is going to add an entire rectangle of area underneath our function that we didn't originally have. So the integral is what's going to figure that out for us. Okay, so the integral from a to c of f of x, actually we did that in part A, so I'm going to just go cheat and snag it rather than having to split up and do those separately again. So we know that's 2, but otherwise you'd go a to b and then b to c. So we have 2, and then the integral of 2 is 2x. I need to evaluate from a to c, which means I get 2 plus 2c minus 2a. And that looks like a great answer. Again, you can do this one graphically. You can say, okay, I'm looking for the area of that rectangle I just stuck underneath my function when I shifted it up. So if this is a, and this is c, and this has a height of 2, your area is going to be c minus a times 2, which is what we got here. When you distribute that 2 in, you'll get 2c minus 2a. Okay, average value, two average value questions. So this will remind you, I hope, of the average value equation. If I want the average value of f on AC, I'm going to take the integral from a to c of f, and I'm going to divide it by the length of the integral, interval, not integral, which is 1 over c minus a. This integral from a to c of f of x, I think we just looked that one up right here, is 2. We did that in the very first part. So what I end up with is 1 over c minus a times 2, or 2 over c minus a for that one. For the last one, we want to find the average value of f plus g from a to b. So we're going to integrate from a to b f of x plus g of x, and we're going to divide by a minus b. You can absolutely write that all over a, I'm sorry, I just wrote it backwards, b minus a. Let me get it in the right order. I just don't like how big that gets, so I tend to write it out in front. Okay, and then integral from a to b of f plus g. Did we do that? No, we didn't, but we can do it fairly quickly. Okay, so we now have 1 over b minus a, and we can split this up. We can go from a to b for f of x, and then we can go from a to b for g of x. I still think, I always get tangled in it when I do the first video for this section, that this one is graphically the hardest to picture. So again, what we're saying there is that the area under f plus g, the sum of the two functions, is the same as the sum of the area under f and the area under g. And really the reason that's true is because when you add two functions, it just stacks their y values on top of each other, which means that if you're looking at a rectangle, you can imagine it as the area of the rectangle that would work for f plus the area of the rectangle that would work for g. Okay, so integral from a to b of f of x, that is 9. And then the integral from a to b of g of x is -2. So it looks like we're getting 7 times 1 over b minus a, or 7 over b minus a. Hopefully that makes sense. Thanks for watching.